Hello, welcome to a new lecture. In this video, we will discuss method of winters, all winters. In our previous video, we discussed simple and double exponential smoothing. Remember that we use those methods when our time series is constant. That's when we use the simple exponential smoothing. But if there is a train, we use the double or the whole method. However, if on top of the trend we also have seasonalities, then this is when we will use the whole winters method. Okay, so as I just said, we will use the method, the winters method when there are seasonalities. So let's understand the way the seasonalities behave. All right. So in this time series, that we have here, we see a behavior that is not random. You see that there are some peaks, and then every cycle we have a peak here, right? And we also have some observations that are, like way below that value within each cycle. Well, that is not that it's not that simple just to define that this is a time series with seasonalities. We need to check also that the point where we have the peak value is consistently located within the same period at each cycle. So, for example, in this problem, we have monthly data, right? So 1 year, the year one will be this one up to here. Year two will be at up to month 24, 21, 22, 23, 24 here. So now if we check, for example, for the first cycle, the peak is in the month 4, right? 1, 2, 3, 4. Now, when we move to the next cycle, so we have something similar. If this is where this is month 12, right? So that's the end of the first cycle. Then this one is the first month of the second cycle, right? So we have 1, 2, 3, and 4. And again, here the peak is located at year 4. If you check the third cycle, you notice that you have the same thing, right? We're having the peak at the same period 4 or month 4. So they don't have to be exactly the same, but the idea is that we have a pattern here, right? We see that the peak and the behavior within the cycle, it's repeating at every cycle. So that's what we call seasonalities. So they're common in different industries. For example, we talk about retail. A lot of products, they experience seasonalities throughout the year. I have mentioned before in previous videos that, for example, school supplies in some specific months, right? They will have some peaks, while in other periods it's going to be low, the demand for those products. In services, such as in tourism, if we talk about like air passengers, hotels, reservations, Airbnb, and similar services. So we also will have some seasonalities. Now, seasonalities are not just like monthly or quarterly. They can be also like even within the week. Like, for example, if we are standardizing Uber rides or Lyft rides, they have the behavior of the demand is not like stationary, it's not exactly the same throughout the week. It depends, like which day, if it's a weekday, if it's a weekend, if it's morning, if it's at night. And if we model it, most likely we will see like there is some sort of seasonality within the week. So yeah, seasonalities are part of time series, and they can be, like they have different time resolutions. Okay, so in the case of seasonalities, they can be additive and also multiplicative seasonalities. So how to distinguish them? In the case of the additive seasonality, for example, here, if you see here, the distance between the peak and the lowest point within each cycle, it kind of like remains the same. It's not changing. It means that even though the time series is increasing, if you see this, the amplitude of the wave is not increasing. So it's additive. That's why we consider it additive. It's like a linear seasonality. However, if we have this behavior like in the second plot, which looks like a ball whip, where you see that it's amplifying, the distance between the maximum and the minimum per cycle is increasing, right? It suggests that this is not a linear process. It's more like a non-linear, seasonality is multiplicative. So it's going to change the way in which we model the time series. So in the Winters method, we will also have the level, which is like the constant component of the time series. We will have t, like uppercase T as the trend. So we can model increasing and decreasing behavior in our previous examples. It's increasing, but you can also have seasonality without slope. That's possible, right? That will depend on the time series. But of course, the new component here is that now we have an S element, which refers to the seasonalities. So we will have an S value per each period within the cycle. So let's say that we are analyzing, our cycle is 1 year, and we have 12 periods here. So that's how our seasonality occurs. Then we will compute 12 seasonality values. If our cycle is 1 year, but we have quarters, then we'll have 4 seasonality components here, right? So you need to compute 4 different values in that scenario. Okay, so this is the main change. And of course, since we have like exponential smoothing, so remember before we had alpha and beta, alpha for to smooth the level, right? Beta to is trend smoothing, and now we have gamma for the seasonality. So since this is like the additive scenario, so if you want to make a prediction or even for fitted values, then the prediction and intention is going to be the level, the last level that you found, plus remember h, it's like how many periods in the future you want to predict. Like if it's like 3 periods in the future, so h equal to 3, t the trend, the last trend that you computed, plus, and this is new, this is the seasonality, and you see here like a weird sub-index here, like t plus h. So I don't want to get confused with this. So you just need common sense. So for example, if you're gonna predict like next year, month of January, so this means that you cannot use, the previous seasonality, of December. It means that you have to go back one cycle completely. This is what M stands for. So you will use the seasonality for the same January, but from the previous cycle. So it's common sense. It's like you're not gonna mix seasons. If you're gonna predict a period that it's located in the second season, then you need to use the seasonality factor, the second season of the previous cycle, right? Which is the last that was computed. So that's pretty much it in regard to the equations. In the case of the additive scenario, in the multiplicative, we have some changes here, and also in the structure of our equation for prediction. Since this is not linear, now we have like L plus HT, like this is similar. What's changing now is like the seasonality factor is multiplying. It's multiplying. So typically the seasonality between will be like around 1. So if it's below 1, it means that it's like low demand in the cycle, low values in the cycle. If it's greater than 1, it means that most likely that's the peak, right? So in our previous example, even though this is additive, but let's assume for a second that this is multiplicative. So if you compute the seasonalities, then the highest value is going to be located in period 4. Okay. So for the residuals, it's the same idea. It's just YT, like the real value in the time series minus the prediction, right? But now you have to consider this is not the factor, right? Same idea as the previous slide. So you have the last level that you computed, the latest trend that you computed, and not just the previous, it's not t minus 1. This is the seasonality factor that was computed in the previous cycle. So they have, again, as I mentioned before, you have to be consistent. If you're computing an error for, let's say, quarter two, so you need seasonality factor of quarter two of the previous cycle. You cannot mix quarters or months. I think that that's common sense. All right, so let's go over a couple of examples so we can apply what we have learned in the slides. All right, so we will be using same libraries, pandas, vector for visualization, stat models for time series, and the exponential smoothing method, which can accommodate, like all methods, simple, double, and winters, which some authors call triple exponential smoothing. Because, there is an additional component. Okay, so in this example, we're going to analyze quarterly electricity consumption for a mid-sized city over 15 years. We have our equations here. So let's visualize our data. So we have quarterly information. And we see some peaks here in the third quarter, like quarter one, quarter two, quarter three. This is quarter four, and then again quarter one, which is like the lowest value in the cycle. Quarter two and quarter three, again, we have the peak. So this is a city with during summer, they need some, AC. So that's why the electricity consumption increases, and they have some mild winters. So that's why during winter, the electricity consumption is at the lowest point. All right, so you can see that this is not random, this behavior. However, you need to confirm that. There are different ways. So just by using a simple plot like this one, so what I'm doing here is like every year I'm plotting the quarters. Since this is increasing, if you remember, since there is a trend here, so I'm just, for each year, I remove the mean value. I compute the mean and I remove it. So now we can compare them. So as expected, in the quarter one, we have that's the lowest value, and quarter three, we have the highest value, and that's consistent, right? Again, they don't have to be exactly the same. So what's happening is just that the pattern preserves throughout the time series, right? So the peak is always located at Q3 in this case, and the lowest value is located at Q1, right? Of course, in a time series, especially if you have a lot of data, sometimes there are randomness, there are other variables that may affect, and maybe for one specific period that doesn't happen, let's say that for, like the year number 5, something occur, and then the highest value is not located in Q3, it's like slightly below. Things like that can happen in real life, right? When you have like messy data. And so you are not going to discard the whole thing just because a single value. It depends. You need to evaluate, like if you have to change the whole thing or not. But most likely you won't for based on a single point. Okay, so let's get started with the first analysis for this problem. So let's use exponential smoothing, which again is the same method regardless you're going to use double, simple, or winters. So you need to define your data. So we're splitting data, right? And then, so we add trend. So we say that the trend is additive. There is a trend because if you check the time series, it's increasing. I don't know, it's not like a constant value. Seasonality. So here we're considering that it's additive too, because when you check the data, you see that it's not amplifying really. Again, there is some randomness, so this is not like a math question that they have to be exactly the same. You need to check the pattern, not the exact values. And the pattern here is that it's not amplifying. The wave is kind of like keeping the same length. All right, so let's continue. So when we define the parameters, here. The trend, seasonal periods, I have to say how many periods we have here. Since this is quarters, m equal to 4. If our cycle has 12 months and we're analyzing the monthly data, then seasonal period will be equal to 12. So this is important because this defines how many seasonal values you're going to find. All right. So we feed our model, and let's go over the table with the details. So here we have the period, the real value, the level, the trend, and the seasonal value estimation. So in this period, we don't have estimations of the y hat, the fitted value, because we don't have previous cycles. And here we don't have y hat for the first 4 periods because there are four quarters, right, per cycle. So once we have that information, we can start computing y hat in the second period. All right. So remember what I told you about computing the fitted values and the forecast. So this one, for example, this y hat comes from the previous level, this one, plus previous trend. And then we need to add the previous seasonal value. But the previous seasonal value cannot be mixed. I mean, I cannot use this one because it will be of the 4th quarter. But period 5 is quarter 1. So, like that doesn't make sense to mix the quarters. So you have to go back all the way until the previous Q1 that was computed, which is this one. This is the one that is used here in this forecast. So for L and T, you use the previous one. But for the seasonal, you need to use the previous seasonal value that was computed in the previous cycle, not in the period right before. Because then you will be mixing seasons, and that doesn't make sense. All right? So once you have computed the information, so L and T will be here, and the seasonal periods are going to be also in the last 4 periods that you have. So now you can use the prediction of the equation. Since this is an additive model, we just add up the values. So here we have how to compute this. So we have L, we have H times T, and we have the seasonal factor. So for forecast of period 49, so we have L plus 1 time the trend. In this case, minus because it's a negative seasonal factor. And remember, it makes sense because if you remember, Q1 is the value in our series. Always Q1 is the lowest values within each cycle. So if you check Q1s, they are negative, and they are always like the lowest value within the cycle. All right, and so that's how you get the calculation of your y hat here, and then you can of course measure the error. With that, we can compute the different metrics to evaluate the model performance. So here you can see the forecast, right, which follows the pattern, right? But that's not the way in which this is important. This is a visual validation, but more importantly, is to measure the real metrics, right? So when we do that, we get that the mean average percentage error is 1.65%, which is a small error. It means that our model is fitting the time series in a good way. We can play with gamma. And remember, for cross validation, we have used 2 methods. Just a very basic cross validation, splitting the datasets in 2 parts, one for training, one for test, or the expanding window, where we start with the minimum values of observations. Here we have 24. So we train with the 24, but then we evaluate in the next one, number 25. Then we expand the window. So instead of 24, we take 25, we train the model, and we evaluate in observation 26. And we keep going that way, expanding the window for training and evaluating in the next observation. So at the end, you get, the 2 metrics one for the classic train test split, or and one for the expanding window, using cross validation. In that case, we got an error of 121%, which again is very small. So it's a good method. You can compare them, you can go into more details. Now, for example number two, here we're going to use a multiplicative scenario. So it changes some of our equations change, especially for the forecast. Is that is not just the sum of the components. Now you have L plus HT times the seasonal factor. Okay, so if we visualize, remember that's always the first step. So you can see that it's amplifying. If you check the initial values, the wave at the beginning, the amplitude of the wave was smaller, but it's increasing, 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 right? So if you compare the last cycle of the last two cycles with the first or the first two, you can notice the difference, right? That the distance between the highest value and the minimum within each cycle is increasing. So this is a sign that this is not an additive seasonality, it's a multiplicative seasonality, it's non-linear. So when we are training our model, here in the seasonal parameter, instead of additive, we use multiplicative, right, to capture that. So we proceed and we do follow the steps. We create our tables to fit the values, we make predictions, and we evaluate. Of course, in the predictions, we need to use the new equation, the sum of L and HT times the seasonal component. All right? Then finally, we can just compare our methods. It means like using multiplicative and additive in the last time series, in number two, just to see like what's going to happen. So of course, in the case of the multiplicative polynomial, we're getting a better performance. In the additive, we get 9.16%, while if we use multiplicative, it's 6.81%, which is smaller. Especially, you can think of this just like 2.6 percentage points. So it looks small, but if you measure like what is the percentage of the reduction, it's way higher than that. And it makes sense because if you look at the initial plot, it follows a multiplicative pattern, not an additive pattern. All right? Okay, so I'm gonna stop the video for now. I'll see you in our next lecture.